Hi, this is a video where we're going to look at ATP production in cellular respiration and where we get all the ATP, what's the total amount of ATP we get from one glucose molecule as it's processed by cellular respiration, and we're going to kind of trace back to each stage the processes and steps and chemical reactions that actually enable cellular respiration to produce that ATP. All right, so here we go. So if you look at this figure right here, you'll notice that we're getting 36 ATP total being made. All right, and each stage, glycolysis, pyruvate oxidation, the Krebs cycle, is indicating how much output we get, and then we add all that together to get 36 ATP. So by the time we're finished this video, we'll actually have this figure figured out. Now, before we actually move too far ahead, I want to just skip to this particular figure right here. And this is the one that we've been using in class. This is of the electron transport chain in chemiosmosis. So here is the electron transport chain, and here's ATP synthase where chemiosmosis is actually done. And you'll notice that NADH is right here. And so what happens is NADH gives an electron to the electron transport chain, and it moves along this path that I'm tracing out with the cursor right here. As that happens, we pump 1, 2, 3 protons into the intermembrane space. Now all 3 of those protons are going to pass through ATP synthase here, and for every one that passes through, we're going to get an ATP. So that means one NADH molecule pumps 3 protons, and for every one of those protons we get an ATP. Every NADH will then make 3 ATP. Is that an exact amount based on experiments? No, but that's kind of the ratio that we're going to use in class. FADH2, you'll notice, gives electrons to ubiquinone, which is the second molecule of the electron transport chain, and it skips this first molecule, which is NADH dehydrogenase. So electrons from FADH2 will travel along this pathway here, but it will only get 2 hydrogen ions pumped. And that means when they pass through ATP synthase here, we're ultimately only getting 2 ATP out of FADH2 instead of 3. Okay, and that'll be an important idea when we look at glycolysis here. All right, so glycolysis will produce 2 ATP net, and then we'll also produce 2 NADHs, which will produce 4 ATP. All right, so if we jump to glycolysis, which is right here, we make ATP here, and we make ATP there. That's 4 ATP that we make in the latter stages of glycolysis. Now, of course, if you recall, we use 1 ATP in reaction number 1, and we use 1 ATP in reaction number 3. So we use 2 ATP, we get 4 back, and that's 2 net that we get out of glycolysis. So if we jump back to the first screen here, this is why it says 2 ATP. All right. Now it also says that we get 2 NADHs out of glycolysis. So if we go back to glycolysis here, you'll notice that in reaction number 6 here, we get an NADH from one G3P molecule, or glyceraldehyde 3-phosphate, and we get another NADH molecule right here out of the other glyceraldehyde 3-phosphate. So this is why it says in the figure that we get 2 NADHs. Now, when those NADH molecules go to the electron transport chain, they will be processed and be used to make ATP. All right. So it says here we get 4 ATP. Now, a moment ago we said that one NADH molecule will pump 3 protons, and that means we should get 3 ATP being made by chemiosmosis. But when you look at the figure, you'll notice that, hey, there's 4 ATP made from 2 NADHs instead of 6. So what's up with that? So we jump to this figure right here. You need to remember that glycolysis is happening outside of the mitochondria in the cytosol. And any NADH molecule that is made in the cytosol has to be pumped across the membrane of the mitochondria, so it can be processed by the electron transport chain, which happens along the inner membrane. Now, specifically, NADH really doesn't have a way, so I just draw NADH here, doesn't have a way of getting across the membrane and going to the electron transport chain inside the mitochondria. So what happens is, as that form of energy is moved into the mitochondria, what happens is the NADH is changed into FADH2. All right, and I'm writing that right there. So we changed into FADH2, not very good writing. So NADH gets changed into FADH2, and that's what makes it into the interior of the mitochondria. And so it's the FADH2 that gets processed by the electron transport chain for ATP production, not NADH. So you jump back here, this is why we get 2 ATP per NADH, because before NADH is not processed by the electron transport chain. Instead, it's going to be your FADH2. Right? So 2 FADH2s make the 4 ATP that are there, and not NADH directly. So that's why we get that difference. All right. Next comes pyruvate oxidation. So we jump down to pyruvate oxidation here. The 2 pyruvate molecules right here that we get from the end of glycolysis, they're going to move through the mitochondrial membrane and into the matrix. And you'll notice here we don't get any ATP being made directly by substrate level phosphorylation. Instead, we get 2 NADHs being made. Well, if we have 2 pyruvates, this happens twice, and that means we get 2 NADHs being made. And if we jump back to the original figure, you can see right here 2 NADHs. Now those 2 NADHs are going to go to the electron transport chain. Again, we're going to go back here, and they'll dump off their electrons here. We'll get 3 protons pumped, and we'll get 3 ATP out of that. And that means 3 times 2 gives us 6 ATP. And, well, 2 times 3 gives us a 6 ATP, which is what's listed right there. So we get 2 NADHs, we get 3 ATP for every NADH that came out of the pyruvate oxidation, and that means we get 6 ATP. Now in the Krebs cycle, we get 2 ATP right here that are made by substrate level phosphorylation. And here's the Krebs cycle, and you get that ATP production happening right here on the bottom. All right. So for every acetylcoenzyme A that comes in, the Krebs cycle is going to turn once, and we're going to get 1 ATP being made by substrate level phosphorylation. So if you recall, when pyruvate oxidation is done, we have 2 of these acetylcoenzyme A's going through the Krebs cycle. So that means we get 2 ATP being made. And we go back to the original figure there. This is why we listed it as 2. Now it also mentions that we have 6 NADHs that are made by the Krebs cycle. Again, if we jump to the Krebs cycle again, you can see that NADH is being made here. That's 1, 2, and up here at reaction 8, that's 3 NADHs. So that's for 1 turn. The Krebs cycle is going to turn twice for every glucose molecule, because we get 2 acetylcoenzyme A's entering it, and so that's 1, 2, 3 times 2, that's 6 NADHs. And if we go here again, 6 times 3 ATP gives us a total of 18. All right. Remember, every NADH that enters the Krebs cycle, the electron transport chain, except for the ones from glycolysis, are going to make 3 ATP. So 6 times 3 gives us the 18 ATP. And then we also get 1 FADH2 being made, which is right here, and that happens once for every turn of the Krebs cycle. Again, if the Krebs cycle turns twice, we should get 2 FADH2s. And if you jump back to the original figure, you can see here 2 FADH2s being made if 1 glucose goes through cellular respiration. And again, 1 FADH2 is going to pump 2 protons. We get 2 ATPs out of that, and 2 times 2 gives us the 4. And then when you add all that up, you get 36 ATP. Okay, so hopefully this clarified some things a little bit. and we'll see you in some future videos. Okay, take care.